In this video we will be dealing with a problem involving a pulley with mass and a block on an inclined plane. This is a block with mass M 7 kilograms attached by a physics string, that is a string that's unstretchable and has no mass, to a pulley of mass of 10 kilograms, radius 0.25 meters, and moment of inertia of 0.4 kilogram meters squared. The fact that they gave me the moment of inertia here tells me that this problem probably involves the fact that this pulley is a non-uniform pulley, and so the formula 1/2 mr squared is not only not correct for it. I could check that since I have the mass and the r, but they've told me the moment of inertia. The block is released and slides down a frictionless inclined plane with an angle of 60 degrees of inclination, so this is 60 degrees with respect to the ground. Draw a free body diagram for the block and the pulley. Alright, nothing very complicated about that. Isolate the bodies. So there's the block. There's the pulley. You want to inventory the forces. There is a weight going down from the middle here, W. There is a weight due to the pulley, WP. Any normal forces? Yes, there's some normal forces here. There's a normal force like that. And this normal force due to the pivot, but I don't know what direction it is, so I'm going to draw it as two forces, an X and a Y component. There's the X component of the pivot axle for the pulley, and there's a Y component pushing up. Put together, and use Pythagorean, I can find the magnitude of the axial force. Friction? Nope. Tension? Yes, there's tension. There is a tension force this way, we'll call it T. And that tension is coming off of this pulley like this. Alright, so weight applied, normal, tension, friction. You got to want the force, 1F. Then you need to put in your axis. For an inclined plane problem, we know that we prefer to put our axis along the plane so that the problem becomes a one-dimensional and the acceleration in y is 0. We're still doing that in this part of the course. For here, we have an axis that we want to put. There's our axis. This is X, this is Y. We need direction of positive rotation, and we want to connect the motion of this pulley to the motion of this block. When this block goes this way, this pulley rotates that way. So we want to make this our direction of positive torque and positive rotation. Now, last but not least, critical angles and dimensions. This dimension right here is important. That's theta. We need that to break vectors into components. You also need this angle. So, not a very hard thing to remember how to do, but back in geometry classes, when you take a transversal line and cross two parallel lines, alternating interior angles are congruent. So this is 60 degrees. That means this is 60 degrees. And that's this angle right here. So that's theta. Now it turns out we won't need that for torque or anything else, but if we were trying to find the forces, for instance to find the axial force, we would need that. And last but not least, you need any critical dimensions, and there's a critical dimension right here, R, the radius of the pulley. You need that to calculate, for instance, the torque here, because that's its moment arm. Alright, so isolate the body, inventory the forces with 1F, draw your axis with the degree of rotation, and find and place all critical angles and dimensions. Do that for every free body diagram. In B, they asked me to use that free body diagram to find the acceleration of the block. Well, turns out that that's not a really hard problem as long as you do everything right. Sum of the forces in X is equal to the mass of the block times the acceleration of X. Reading the diagram, I have W sine theta minus tension is mass times the acceleration of the block. That's equation 1. Unfortunately, I can't solve that because of this tension. I don't know it, so I can't solve for AX. In terms of torque, however, with the pulley over here, we have that if you count the sum of the torques about the center, that's equal to the moment of inertia about the center times alpha. For the torques, about this point here, the only one of the forces that creates a torque is this tension, and it's TR. And it's in the positive direction. And that has to equal I times alpha. But we have a no slip. Alpha times R is equal to AX. This is the no slip condition. This point on the rim has a tangential acceleration of alpha times this radius. But it's also touching the rope. And because the rope and it are moving together with no slipping, they have the same velocity and the same acceleration. And we call that rope acceleration the acceleration of this block, and we gave it the symbol out A sub x. So A sub x has to equal the tangential acceleration of the rim, and that's alpha r. I'll multiply both sides of this equation by r, and then put in A sub x, or if you prefer, you can simply substitute in for alpha. I'll substitute in for alpha. So let's say if I do this, I get IC AX over R, and then I'm going to divide by another R to get the R from this side to that side. This gives me that the tension is the moment of inertia divided by R squared times AX. So remember that the moment of inertia looks like something times mr squared. So when you divide by r squared, you're basically getting the effective mass. So force is ma. Now this equation is equation 2. I want to combine that with equation 1. And I'm going to do that by add 1 and 2. When we do that, we're going to eliminate t because we have this minus t. And here we have plus t. So we get mg sine theta. The t's cancel, and we get m plus ic over r squared times ax. So ax is mg sine of theta over m plus ic over r squared. Now what have I really done? This is the force, the external force, and this is the effective mass, the mass of the block, but also I have to account for the fact that I have a pulley, and it has an effective mass that we're having to move. So it's the total mass times ax. So back in earlier in the course we didn't have this term. We just had mg sine theta is max, and we cancel the m's. Now we can't do that. Putting our numbers in, if you do that, I come up with 4.43 meters per second squared for the acceleration of this block. I'll leave putting the numbers in for you. The next part asks, what's the tension in the string? Well, the tension in the string can be found either by solving this equation for t or solving this equation for t. And I'm going to tell you what, I'm going to do this equation number 2. So t is ic over r squared times ax, which makes it approximately the moment of inertia of this thing was 0.4 kilograms meters squared, and then we divided by 0.25 meters, which we squared. That killed those guys, and then we multiplied that by 4.43 meters per second squared. And when I did all of that, I came up that it was 28.4 newtons. If you use the other equation, equation number 1, you better get the same answer. If you don't, then that's an indication you made an algebra mistake. It says, what is the angular speed of the pulley after the block has been sliding for 5 seconds? Well, the alpha in this case, remember the alpha in this case is AX over R. And I'm not going to actually plug numbers probably until later, but the point about it is this. The AX is constant. The R is constant. So this is constant, this is constant, so it's constant. And since it's constant acceleration, rotational kinematic equations are true. So omega is equal to omega naught plus alpha t using big board. So I replaced v with omega, v naught with omega naught, and acceleration with angular acceleration. It starts from rest, so the pulley wasn't initially rotating. This means omega is equal to AX over R times t, and that's 4.43 meters per second squared divided by 0.25 meters, and then times 5 seconds. And when you do all of that, you come up with 88.6 rad per sec. And that's the answer to that. And that's all there is to this problem. See you on another video.